point actually comes directly from this aquaculture science book, but I tried to jazz it up a little bit. And I want to talk to you guys a little bit more about your experiences with the recirculating system that you guys have at your school. And so recirculating systems have been around for actually the past 30 years or so. And originally they were implemented for research purposes because they're enclosed systems. Scientists can easily do experiments, things of that nature. But in the past decade or so, they're gaining a lot of popularity, especially for culturing different fish species like food fish species. So I wanted to talk to you guys about some of your experiences and what you think some of the advantages and disadvantages of using recirculating systems are. So when you guys were putting yours together, what were you thinking, like, oh, this is awesome for our system, or maybe we shouldn't do this kind of thing?
No, I mean, I thought it was all pretty cool. I mean, you can do a lot of food in a really small amount of area.
So area size is decreased. Any other advantages, maybe? All right.
You have to deal with other wildlife.
So you're in an enclosed type of system. You can stop outputs from maybe like weather, things of that nature. So some of the advantages that we've come up with is the reduced amount of water. So recirculating systems are circular. You're continuously flowing water from tank to tank through a filtration system and then back through the tanks. It's a little bit different from those flow-through systems where in flow-through you have water entering the system and then exiting the system, and new water is coming in and exiting and so on. So in this system, it's constantly recirculating, it's cycling through.
A good example of flow-through systems, catfish ponds in the Mississippi Delta, big ponds, raise catfish, because they have a big supply source of groundwater. As opposed to the mountains in North Carolina, for example, where you actually have trout, rainbow trout production. Those are raised in raceways where you have a lot of spring-fed rivers and waters that flush that water through the system with rainbow trout. So those are flow-through systems. You need a lot of water.
You do need a lot of water for those types of systems. And with the raceway systems, you reduce that amount of water that's necessary.
People like set those up in rivers or wherever, like if you had like a raceway, people set those up in like a river.
Well, you have to remember that, then you get into a lot of permitting issues. And I mentioned the mountains of North Carolina. That's a rather unique, interesting industry there for rainbow trout, where they're able to use those spring-fed waters. But yeah, you have to think about the permitting issues also with obtaining water to use it.
Another thing is that you can control the environment. So oftentimes these are in enclosed areas. So that means you're stopping them from being in adverse conditions. So like snowfall or really hot temperatures or maybe hurricane conditions, you have it in an enclosed building. It also allows you to control, say, water temperature or salinity, things of that nature, because you're not bringing in new water sources. You kind of are just recirculating the water source you have and monitoring that water quality. Recirculating systems also offer the ability to have year-round production. And again, that's because you can manipulate the water environment. So keeping those fish either ready to spawn, or maybe you have broodstock that you're prepping for spawning. Some more advantages is that you can use existing buildings that already are there. So you might decide to set up your recirculating system in a warehouse or some other pre-existing structure like a greenhouse. You also have, again, higher yields of product per gallon of water that you use. So you're reducing the amount of water that's used in the system. You have improved feed conversion ratios. And so what that means is that you don't have to feed them as much food as you might necessarily do in one of those raceway situations. So in raceways, typically what's done is they feed out and they might feed so much food where the fish eats 10 to 15 minutes. And then after that, if all the food's gone, they might feed a little bit more. If it's not all gone, that's how you know you stop. They're not hungry anymore. With this, what you can do is you reduce the amount of feed, but you're still getting that same amount of growth or input product that you're looking for. Another thing is reduced reproduction. So we're saying you can have year-round spawning or year-round production, but another thing you want to look out is reducing reproduction in that you're only reproducing when you want to. So you can look at, say, different temperatures. So for shellfish, you might keep your broodstock colder. And then when it's time to spawn, you'll slowly warm that broodstock up and then they spawn for you. So that's how you're reducing reproduction to only times that you want to. Next up, we're going to talk about some disadvantages. So when you guys were putting together your system, did you come across any problems?
So
It's expensive. Any other disadvantages that you might have come across?
that was a main thing. Budget.
Budget, okay. So typically for commercial use, again, it's that high initial investment. So you're buying tons of tanks, you're buying all your PVC piping, your filtration system. So you might have to get UV systems or pumps. You might get a protein skimmer. We'll talk about those things later on, but that initial cost can be quite expensive. And if you're starting to culture either maybe a new species or you're not familiar with culturing these products, you might have a lack of success because, again, it's your first time doing it. So lenders might have some issues when it comes to lending that money initially. Also, systems can be very simple, but if you're going commercial scale, they may become very complex. So you're adding on additional tanks. You might need a larger pump. You might need more air stones or a bigger blower. So those are all things to keep in mind when you're going into commercial use. And since the water is recirculating in these recirculating systems, it's very important to look at your water quality. You might see things like ammonia and carbon dioxide entering your system, and those are things that you need to start reducing, and that's because it can lead to poor water quality and the death of your fish. And if you're doing this for commercial reasons to gain money, you don't want your fish to be dying, right? And so that's why you really have to pay attention to your filtration methods. And sometimes if you're not paying attention to that, there might be inefficiencies, whether you're not, say, cleaning out your filtration bags. If you're not paying attention and your UV bulb has burnt out and you haven't replaced it, things of that nature. So that's some of the disadvantages you might run into. Next, we're going to go over some of the system design. And I wanted to know what was your design of the recirculating system that you guys built? So what kind of structures did you use?
We used like, I don't know what the gallon size was, but it was a big black tank.
Big black tanks?
Just, like pumped water into a it was a 55-gallon barrel.
Okay.
And a clam bag full of bioballs.
Bioballs.
So that's your biofiltration. So
Mhm.
you thought about biofiltration. That's one component.
And
That's good.
then it goes back, I'm pretty sure it just goes back into the water after it filters out.
Okay.
We have a bunch of air stones.
Air stones, so aeration.
So that's aeration, another component. You mentioned the first component, the tanks.
Tanks.
Oh, no.
That's okay.
You gotta feed them.
Yes, you do have to feed them every day, and we'll go over what happens when that food breaks down. So we're going to be talking about the removal of ammonium and those solid wastes that occur. So you guys got those. And so that's actually the basic components that we'll be going over is the different tanks, solid filters, so how to remove those waste products.
Your head was good up there.
Biological filters, aeration, and then the buffering systems.
So you pretty much addressed all that in your system.
So there are 4 types of waste solids. We have settables, suspended, floatables, and dissolved solids. And I want to ask you guys, where do you think these waste solids come from?
Fish poop and uneaten food.
Exactly. So we have fish poop, uneaten food, and urea. So that's the fish pee as well. And that's where those solids are coming from. And the first one we're going to talk about are settleable solids. Do you guys know what settleable solids are? Exactly. Just follow the name. These is the easiest of the 4 to remove, and exactly what you said. They settle out of the water column. Typically within an hour or so of them entering the water column, they'll settle out. You can either have them settle to the bottom, and at the bottom of the tank have a drainage system where you just remove the solids that way. Or what you can do is actually resuspend them. And as you resuspend them, they exit your tank into either a sedimentation tank or a clarifier like this. So in A right here, you have your wastewater coming in, or your tank water coming in. It actually settles out at the bottom here, and you can have it exit out that way. So that's how the clarifying tank would work. What kind of did you guys do in your tanks to remove waste?
We had like a constant whirlpool.
Constant whirlpool.
Yeah, everything was just kind of up and moving.
Okay, so you were doing the resuspension.
Mhm.
Okay. The next one is suspended solids. So this is different in that it stays suspended up into the water column. The way you can remove these is through mechanical filtration. So using screens or granular media. Right here, we actually have a bead filter. So what happens is the water enters the system, and as it goes pushing outwards, the beads actually capture the particles, the solids. And then what you would do is you would backflush the system, and the solid waste would all fall to the bottom and create a sludge, and that sludge is what you would then drain out of the system. Nowadays, they actually have bead filters that automatically backflush, and you just have to open up the valve and the sludge comes out. It used to be that you'd have to connect a whole nother hose to it and then wait for it to backflush out. So the next one is to remove foam, fine, and dissolved particles. So these are particles that are microscopic. They're about 30 micrometers in size. So you really can't see them, but they actually make up about 50% of the volume of just waste solids that you find in your system. So they are very important to move. And so an example is using the protein skimmer. And basically what happens is water is my mouse working? Oh, my mouse died. Water right there is moving into that bottom of the tank or that column there, and air bubbles start at the very bottom of that column. And as the air bubble travels up through the column, it's actually trapping those particles. It then goes at that top where all that foam culmination is, or the waste effluent. So that's where all the bubbly waste, all that excess protein is, and that's what you would remove from the system there.
So when you go to the beach and the waves break on the shore, you see that foam? That's a natural protein skimmer. So those dissolved organics in the seawater are being stripped out when the waves break on the shore. You've got aeration, it's pulling it out. That's what the foam is. It's kind of that's a good example of what that's doing on a much more mechanical design level.
Correct. Where do you guys think all these proteins are coming from?
Small fish waste. Broken down.
The fish waste. So think about the food that you're feeding them. That food is made up of a lot of protein. It's made of fats, some lipids, some minerals, but the majority is protein. And so when the fish leaves that waste behind, so the urea, the fecal matter, that matter is also made of protein. So your goal is to try and remove that protein, and we're going to talk about why. And that leads us to the nitrogen cycle. And so again, that protein is metabolized by the fish. So the fish uses it all up, but what's left is excreted from the gills. And so in saltwater fish, they'll excrete their urea through their gills. In freshwater fish, they actually have a pore that they excrete that from. And some of this byproduct is toxic. So we're going to talk about total ammonia nitrogen, which is called TAN. And that's made up of two chemicals. We have the unionized version, which is NH3, and the ionized ammonia version, which is NH4+. One of those versions is toxic. Do you guys know which one? The ionized one. Any other guesses? It is. It's the other one. 50-50, it's okay.
So the ratio, how that breaks out into one being toxic and one not, depends on the pH and the temperature of the water. So you want to try and maintain that so you have less unionized ammonia.
What pH do fish like?
That's a good question. So I think we addressed pH.
We do.
So we'll go talk about that in a minute.
Okay. So right now we have our total ammonia nitrogen, TAN. And what we're going to look at is the nitrification cycle. So again, we have our fish and food. The fish are consuming that food. The ammonia is excreted out through their gills as NH3 or NH4+. You're worried about the unionized version because that is the more toxic version. But you have bacteria in your system that are going to start to break that down. And so what you have is the ammonia getting break down into nitrites. And that's done by these bacteria called nitrosomas. And so my question for you guys is, do you think nitrite is toxic or do you think it's non-toxic? It is toxic.
Sounds like a bill problem.
Yes. So what actually happens is nitrates, they can be in very small quantities, but depending on what's happening, if you're not having them being broken down, these nitrates actually attach to the hemoglobin. And what that happens, you actually reduce oxygen flow. So oxygen transport isn't really happening within the fish. That means the fish isn't getting enough oxygen. And so basically what happens is it forms this cell called methemoglobin, and it's a dark brown. And so that's where you get brown blood disease. So when you see those gills look brownish in color, that's brown blood disease because the hemoglobin aren't bright red.
Mr. Powers taught us about this. You add the two bacteria to nitrous amounts.
Yes.
You can purchase it to actually see your biofilter, hope it gets started.
Oh, but in a bio.
But they're naturally occurring, you just might take longer for them to build up so that they are effective numbers to do their job with fish in your tank.
I thought you said an add period.
Yeah, we'll go over that a little bit more. But then you have your nitrates, and that's broken down by your nitrobacter bacteria, and that's broken down to nitrate. Do you think nitrates are toxic?
No. Thank you.
Exactly. So your plants are eating them. So that is the nitrification cycle. Something I want to point out, though, is that during this cycle, you're using up a lot of oxygen. There's an increased oxygen demand. So that's something to be mindful of within your system, is that oxygen is being taken out. And that's going to affect your fish if you're not aerating it back in. The next thing is denitrification. So how do we break down those nitrates? And there's heterotrophic bacteria within the system that actually break down those nitrates into nitrogen gas. And that gas can actually be aerated off into the atmosphere. And so that is the complete like nitrification to denitrification cycle. So there are ways to control for the nitrogen, like you were talking about, is using those bioballs. So that's your biofiltration. And so what happens is the way those bioballs work is that it has an increased surface ratio on them. And that allows the bacteria to actually attach and settle onto them. And then the bacteria are within the system and they can start consuming up that nitrate ammonium, right? And so you guys have just used the bioballs there? Okay. And that, yeah, so that is, did you guys actually seed your system with the bacteria as well?
Oh, I don't know. That's what I was wondering. I didn't know if you did that or not.
Okay, so the next thing we're going to talk about, we'll actually get to that, but is increasing that surface area. So you can use a thing called a rotating biological, it's an RBC. And so basically it's these panels, and those panels have those pores on it, and it allows the bacteria to attach. And it's actually rotating. So each panel will dip into the water where the bacteria can be in that water area, and then it'll rotate back out. And so what's actually happening is that you're having an oxygen carbon dioxide exchange. So you're bringing oxygen into the water. The bacteria are also consuming up the ammonia and nitrates. But as you're coming out, the carbon dioxide is being degassed off. So that's how the RBC works. So what's interesting about these is that you don't have to clean them as often as you would think, and they don't take up a whole lot of square footage. So with sometimes like bioballs, things like that, they'll make it a little bit filthy because they'll act as maybe like a bead filter where they're not just breaking down the nitrogen within the system, but they're also having sediment or solids attached to them as well. To start up a new system, you could seed the system. And what we were talking about is they have the two different bacteria up at the top in those two bottles. So you can actually purchase that and seed the system. Typically, this would be done about a month prior to you stocking with fish. Another thing that you could do, it's something called cold seeding, where you have your system already set up and you put fish right into the system. And so you're trying to build up the bacteria within the system. It's not already there. So what might happen is you might have fish die off during the process. So there's different methods that you can do for that. Does that kind of answer your question about how to seed it?
Yeah, you probably have.
Yeah. Next, we're going to talk about pH and alkalinity. So pH is the amount of hydrogen ions within the water column. And then alkalinity is your ability to neutralize hydrogen ions or neutralize the pH within the system. So I was going to ask you guys, what do you think affects pH within your system and alkalinity? Any ideas? I'll take guesses too. So what are a lot of the things we've really focused on right now? We've focused on a lot of ammonia and nitrogen, a lot of food coming into the system. All right, so we have food coming into the system. The fish are breaking it down. The fish are releasing the food into the system. The bacteria are breaking it down. There's a lot of oxygen demand, so a lot of oxygen is being used up. But at the same time, during the nitrification cycle, that's changing your pH. So typically, you're having a decrease in your pH.
Also, fish are in your tank, and what are they doing other than eating and pooping? What else are they doing in your tank? We all do it. We're breathing. So they need
But we're
oxygen.
also-
They need oxygen, and in turn, what are they releasing when they respire? And carbon dioxide results in more of an acidic type of situation. It reduces your pH.
And as that reduces the pH, you might also see a loss of alkalinity as well. So if you're seeing your pH is decreasing, something that you can do is adding some type of carbon source to it. So you might add carbonates, you can actually add oyster shell. So oyster shell is made out of carbonates, calcium carbonates. You might add lime.
Soda ash, bicarbonate.
Could you add just like stuff, because I like pH up and down for water.
You like what?
I have pH up, like for adjusting pH, I have like bottles of that stuff. Could you just like add some pH down to it?
So you have little bottles for your tiny tank?
That's for plants.
Okay.
I was just wondering if it would like shellfish.
Well, we're thinking more on a commercial line here with big tanks, and putting little bottles in probably is
Not cost effective.
So there are other major areas. Oyster shells in the wood, but there's other areas, other solutions that can be added that are part of the system.
And you're asking what a good range of pH would be. Typically, it's around 6 to 9.5. That's a good range for that, but you also have to consider what's a good range for your bacteria too. Because if you have either too low of a pH or too high of a pH, you might kill off the bacteria that are breaking down your ammonia and your nitrates as well.
So to answer your question, Pete, what is the optimum pH to try and maintain? Can you look from that scale there to your right? And we're looking at something between 7 and 8, right?
Yeah.
Try and maintain. Easier to read it.
No, it's great.
Yeah, okay.
We're still good on time. So the next thing to think about is your temperature controls. So depending on what species you're culturing, you might want your water temperature to be warmer if you're, say, doing tropical fish. If you have cold water fish, you're going to want your water cooler. And so the way you can either make your water cold is by using chillers. If you want to make it warm, you might use heaters. Another thing to think about is maybe greenhouses. You could always have it, because that's an enclosed area. The culture tanks could be in a greenhouse. Some, depending on what the system is, you might have it by air control. So just use ACs. That might not be very cost effective depending on what it is you're doing. So you're looking for the most optimum way to either heat your system or cool your system for the lowest cost. But there are different ways to do that. Next is aeration. So again, with the nitrification cycle, you're consuming a lot of oxygen. Your fish need oxygen as well. So you want to make sure your system is being aerated. And so you can do that with air stones, air diffusers. They have agitators, which agitate the water and let air from the surface come in that way. You can use packed columns too. So the main thing is to keep your system aerated. You'll often see blower units. So blowers, they're attached to multiple tanks, systems, and it'll allow air to diffuse into all the tanks and then bubble upwards. Another way to do it is using pure oxygen. So you can do oxygen injection. This is a lot more intensive, but it allows the oxygen to enter the water at a much quicker rate. So that is something to think about. But again, it's a lot more intensive than doing an air stone.
That's just adding oxygen.
Pure oxygen.
Pure oxygen.
Mm-hmm.
So it's expensive and a lot of other controls have to be available
Yeah.
for you to do that because it's highly flammable as well.
So that means having people, staff and technicians trained. You'd have to think of it as being a hazard. It depends.
It depends on, again, what species you're growing and at what density you're growing as to your scale of inputs.
Because an air stone's adding oxygen into the water, but is it doing so at a rate that your tank needs, right? So with oxygen injection, you could get a lot of air stones. Yeah. Next is disinfection. And I wanted to ask you guys, did you have a UV system or anything like that on your tanks? Why might you want to have a disinfection system? Bad bacteria. Yep, to kill disease. So something we didn't go over yet is that in recirculating systems, your water is going tank to tank to tank to tank to tank. In a lot of facilities, they'll have a quarantine area where fish aren't just introduced into the recirculating system. Instead, they're quarantined for a certain amount of time. And that's to ensure that they're not going to be inputting some new disease that the system didn't have. They want to keep their fish happy and healthy. So you keep them quarantined and then you put them into your recirculating system. But say you miss a fish and a fish does have some type of disease. That disease is then spreading from your tank to your tank to your tank to your tank. And so you want to be able to disinfect it. And there could be stuff coming through in the water supply when you're inputting water as well, like different bacteria, things of that nature that you don't want within your system. And so by disinfecting it, you can help remove it. So there's two different ways you could do this. There's ultraviolet irradiation, so UV light. And so basically what you want to look for is a nice UV light that has that surface area, but you have to think about your water flow. If you're going really fast and your water's just flowing super quick past that light, the light doesn't have the opportunity to kill off that bacteria, right? So that's something to think about when you're installing these. What's my water flow rate? Do I have a large enough UV light? Am I replacing my UV light when I need to? If depending on what system you might be using, your UV light might have to be on at all times, only when water is flowing through it, kind of thing. So there's a lot to think about, but UV light is typically the most often used. You could also use ozone. Now, ozone is a strong oxidant. It kind of acts like bleach, but it's a lot more strong. But something to think about is that you have to be trained to use it. It's a lot more intensive. It can be very expensive depending on, so typically it's a lot larger commercial facilities that are going to be using ozone. Now you'll see that there's some other chemicals that you might be able to use. So you might see like use bleach, right, to clean some things in your tanks. You don't often want those things ending up in your water supply. So when you're recirculating, you're not just going to be dumping bleach into them, right? So that's why you typically just see the UV or the ozone being used.
But keep in mind, so if you maintain your water quality at optimal levels, your biofilter system's working well, you know how to adjust for your pH, your filtrations are working well, you're removing the solids. If your water supply source does not contain potential pathogens, or you treat your water supply source first before adding to your tanks, as well as what as Natalie said, all your fish going into your tanks, your fingerlings have already been pre-screened or held in quarantine. If you do all those things, then really disinfection is something that does not have to occur. Your fish can be healthy. And of course, the other component is you're feeding them a good nutrition diet as well.
Yeah.
Right.
So lastly, we've talked about a couple different components when it comes to monitoring your fish system, your water quality. But the main thing is that you have to observe it day to day. What's going on with your fish? Your fish are going to tell you if something's wrong within the system. Like you said, like if you saw the gills turning brown, you might say, oh, I need to look at my ammonia nitrates, that sort of thing. If you see your fish gulping at the surface, you might say they're not getting enough oxygen in the water. Another way you can look at is your solids is this Imhoff cone. So what you actually do is you take a sample of water and you let it sit. And as it sits, those solids start to settle. So you might see how many solids you have within your water column within your tank system. You can also use something like oxygen meters. You have your pH meters that you could be doing as well to test on a day-to-day basis what's going on within your system. And then routine maintenance, because yes, it is recirculating, but at times you will have to shut it down because you need to clean your tanks. Say a disease does break out, you're going to want to clean your tanks out. If you're using different screens or different filtration systems, like where sludge is building up, you're going to want to take those apart and clean them up as well. You might have to add new water to the fish tank. So evaporation can start to occur where, so your system's been running and you have water evaporating off. You're going to eventually have to add new water into the tank. You might want to drain off that older water that's been in there as well. So it's definitely routine maintenance, checking your water quality, looking at your fish behavior. That way you are maintaining a very good recirculating system.
What do they do? Like the fish?
They might have different tank systems. So they might have tank or system A and system B. And they'll have only system A running and system B is not running. They'll clean up system B and get it ready and prepared for the fish to be transferred over. Other ways to do it is recirculating systems can be set up where a single tank can be shut down, but the system itself is still moving. That way you can clean one tank at a time, sort of thing. You can also have it so that depending on your filtration, you can shut down a single filtration device. So you might want to change out your UV system. You can just turn that off for a little bit by having it shut down, and the water will bypass to the next step kind of thing. That way you can change out the UV light. If you have like your bead filter, that'll be set up so that the water can also bypass going through the bead filter back into a separate tank kind of thing. That way you can remove that sludge from the bead filter. So there are ways to get around doing it, but that's where system complexity comes in.
So Natalie just gave you a good overview about recirculating systems. And even though we just said earlier that the summer session is going to be to introduce you to the various Florida aquaculture commodities that are being raised. This isn't an aquaculture commodity, but it certainly is a system that can be used for raising tilapia or other food fish. And you will hear a little bit more about that later with Mr. Evans. Or in other commodities, this is a good system for maintaining your broodstock in a closed system where you want to control their temperature and their diet and so forth to encourage them for maturation. Actually, you know from your clam hatcheries here in Cedar Key that your broodstock tanks are also operated on a recirculating system to hold those clams and to change the temperature so that they would spawn on demand. So it is one of the more complicated processes in aquaculture, and that's why we wanted to start it off with this, and also to add to your knowledge that you're gaining as you actually operate a small recirculating system. And it's not by design that you're using tilapia. Tilapia is one of the most forgiving aquaculture species that you can raise with less risk in a recirculating system. And again, we'll be talking to a tilapia grower as well later in the summer. But to make this a little bit more exciting for you and to see a real large commercial scale operation, we have invited in, is Mr. Brian on? And
yeah, good morning, I'm here. So first, let me introduce myself. My name is Brian Catanzaro. I'm the facilities manager here at our Pace Water facility. It's a aquaculture demonstration facility. We have 5 separate systems. The systems are identified as A, B, C, D, and E. Systems A, B, and C are basically replicates. They're smaller systems that might be used for quarantine, research and development, broodstock holding, purging, things like that. They're not really true production type systems. The 2 larger systems are systems D and E, and they are true production systems. We do produce fish. We can typically produce about 6,000 pounds per crop. We're growing tilapia and hybrid striped bass. I'll give you a quick tour of the smaller systems. They're basically replicates. There's 3 culture tanks, 1, 2, 3. They're each fed to, the water drains to a sump tank. It's pumped through a mechanical filter, biological filter, UV sterilizer. There's some gas exchange. We strip CO2 and add oxygen. So basically these systems are almost identical to what you guys just reviewed in the presentation that we just looked at. All of those mechanical processes are the same. The equipment might be different. We can use different equipment to perform the same function, but all of the core process is the same. Our facility is based on well water. You can see these water storage tanks over here in the corner where my cursor is. We bring well water in, store it in the tank, and it's pumped throughout the building. You'll see up here, if you guys can see where my cursor is, up along the ceiling, we have distribution lines where we distribute low pressure air, oxygen, fresh water, salt water, and municipal water to each one of the systems. You can see where the lines come down the wall right here, and all of those products are fed into the systems as needed. So we have an auto fill valve in the sump that maintains the water level automatically within the system. The systems themselves, what you can see on the back wall here, we monitor oxygen directly in the tank. So each tank has its own oxygen probe. There's a backup oxygen system within each tank so that if the oxygen goes low, particularly after feeding events, the fish might get excited during the feeding events and the oxygen might drop down a little bit. Backup oxygen system will automatically come on and keep the oxygen levels at predetermined set points. The controllers themselves are all online. I can log into the systems. Can't fully operate the entire facility, but I can operate the majority of the facility remotely from my laptop if an alarm condition occurs. So let's maybe walk back this way. I can show you some of the bigger systems. You'll see up here in this corner where my cursor is, we do have an automated feeding system. You can see the rail that runs along the ceiling that goes over each individual tank. There's a computer control right here on the feeder. So we can control the amount of food that is fed to each individual tank automatically. So depending on the species, some fish we feed every 2 hours around the clock. Hybrid striped bass we might feed every 6 hours around the clock. So if we walk out on the back patio, all of the filtration for the larger systems is out on the back pad. So the water drains from the tanks via gravity. This is the main line from the filter. So the water drains from the fish tanks through this line via gravity. It's a rotating drum screen filter where the solids are filtered out. Drains into the sump tank right here. So this is a mixed bed biological filter. That's where the ammonia removal occurs. We also remove a lot of CO2. You can see each one of these boils is an air diffuser where we are using that to mix the media for the biofilter, as well as stripping out carbon dioxide. Move over to a pumping chamber where the water is then picked up through the pumps. It is then pumped through right here, you can see we have temperature control to maintain temperature within the system. So if I can move it over here. Here we have a UV sterilizer along the wall, and then we are using pure oxygen, so we inject oxygen into the cones, and then it's pressurized. The whole system is pressurized. Once the water enters the pump through the UV, through the temperature control, and oxygen injection back to the fish tanks itself. So again, the core process that you guys talked about is all the same for each system: mechanical filtration, biological filtration, UV sterilization, and gas transfer. This is a separate system. Might be a little bit harder to see, but basically it functions the same way. Water is fed by gravity through the drum screen filter. It's then pumped up into this large vessel here, which is a fluidized bed. That's where the biological filtration occurs. It is gravity fed from the biofilter into the top up here. You can see the fan. We're stripping out carbon dioxide. In the middle, we're adding oxygen. This device here is a large low pressure UV reactor, and the water is gravity fed back to the fish tanks themselves. So each one, there's two separate systems. These two tanks over here are the cold water systems, and the tanks over here is the warm water system. One of the other things that I can show you, if I can get to it, we do also utilize a dual drain setup. So in the beginning of the presentation, you guys talked about settleable solids. This device here, the water exits the tank two ways. There's two pathways for the water to leave the tank. One of those pathways comes into this cone here, where settleable solids can be collected and automatically discharged, and then water drains via gravity through this pipe here out to the drum screen filter on the back.
Ryan, I have a quick question.
Sure.
How big are those tanks? What's the volume of those tanks?
So there's two separate tanks. This tank here is 8,000 gallons, and this tank is 2,000 gallons. The tanks in the back are about 1,000 gallons apiece. But yeah, this tank is 20-foot diameter, not quite 4 feet deep, so it's about 8,000 gallons. Here you can see our oxygen monitor. This cool water system uses a slightly different device. This is called a radial flow separator. That's where also the settleable solids are removed. It's a slightly different design, but again, it performs the same function. It's just a different piece of equipment that does the same thing. You can actually see on this tank in the back right here, that radial flow settler is actually part of the tank. It's built into the tank. And let's see. Yeah, so this unit here, you can see this computer control on the wall. It's a touchscreen PLC, or programmable logic controller. So all of the water quality sensors and devices are all controlled through this one controller. So when I can remotely from my laptop log into this device, and I can check on pumps, make sure the water pumps are on. I can check oxygen levels, pH, if the pumps are flowing, things like that, so temperature, and all that can be controlled through this device. So we do have full automation, which is a blessing and a curse all at the same time, because if anything happens, and it does happen, we get phone calls and texts in the middle of the night, 24/7. If anything goes wrong, people have to come in and take care of it. We don't have a lot of alarm issues, but it does occur. One of the other things that I didn't point out, I'm not sure we'll be able to get to it, is I have a quadruple redundant backup oxygen system. So we have an oxygen generator. We generate our own oxygen on site. If that unit should fail, we also have a liquid oxygen tank as a backup. And I actually have two separate liquid oxygen tanks that we try to keep one full at all times. So there's usually one full one and one that might be half empty. So the primary source is the oxygen generator. We have two tanks of liquid oxygen as a backup, and I also have a 16-pack of high-pressure cylinders that if all else fails, I can run off the high-pressure cylinders for probably about 2 days. So oxygen is one of the most critical things that we monitor. If we lose oxygen for as little as maybe 20 minutes, we could lose a crop of fish. So I may have 10 months worth of time and investment in a crop, and I could lose that in as little as 20 minutes. So it's extremely critical in recirculating systems to monitor oxygen as well as have a backup source should anything happen. I do know it works. We did lose, I have a generator that I can power the facility on. During the hurricane, we lost power. The generator ran for roughly 3 hours and failed. Unfortunately, there was a temperature sensor that failed, and my generator lost power after 3 hours. Facility was without power for 12 hours. When I came in the next day, I found there was no power, but we did not lose any fish because of the backup oxygen system. Liquid oxygen does not require power to operate. As the liquid turns to a gas, it doesn't require any electricity to perform that function. So we did not lose any fish during the hurricane because of the backup oxygen system. Once we were able to get power established, get the pumps going and things like that. So people often maybe wrongly assume that, if you lose power, that your water pumps and things like that, your filtration is the most essential, and that's not necessarily the case. Oxygen is the most essential parameter. So if you have a good backup oxygen system, you can kind of weather the storm, so to speak, that if you have other mechanical issues, you can address them, but oxygen certainly is the most critical.
Well, let me stop a minute. Do any of you guys have any questions of Mr. Brian? No? Want to know how much fish he's producing? Anything like that? Is that what he just said? I'm glad you're listening.
Roughly about 20,000 pounds a year. Again, this isn't a true production facility. It's more of research and demonstration. So we are a manufacturer of equipment. So we will test the equipment here in the facility before it's sent out to market. But also, if we go back out and look at the filtration system on this side, that's pretty much a standard design with the drum screen filter and the mixed bed filter, UV reactors and oxygen cones. That's a very standard design in the industry these days. So when we do design full facilities, instead of just looking at it on paper, you can actually come to the facility and see how the design works. And we know it works because we're using it. So while we do grow fish here, selling fish isn't what's paying to keep the lights on. But like I said, we know it works because we're doing it. So this setup here is pretty much the standard of the industry, if you will, right now. It's not just our design, but any of the engineering firms that design RAS facilities are starting to standardize on this type of equipment, specifically the large salmon farms. The majority of the RAS systems these days are based around salmon culture. RAS systems really haven't taken off in the United States as much as they have in places like Norway, Iceland, Scotland, Canada, and Chile, where the major salmon farming regions are at in the world.
Brian,
yes.
Are there any systems for broodstock maintenance or other applications here in Florida that you're aware of?
Most of the RAS facilities in the state of Florida are with the universities or the research institutes like Mote Marine or Harbor Branch. I know the University of Miami has several systems. They have some interesting systems that they're putting in for broodstock. They're actually spawning a lot of saltwater species like grouper, different types of snapper, mahi. They're even working with tuna. I was down at their facility, I think at the beginning of the year, to look at some of their broodstock systems. They're actually kind of creative about how they actually capture the eggs after the fish have spawned. But commercially, probably the biggest facility that's going in is going to be the Atlantic Sapphire system down in Homestead. It's my understanding they should be starting into production at the end of the year. They're still under construction at the moment, but they should be in production within the year. But to answer your question, most of the systems are with the research facilities or the universities.
And tell these young folks here what's going to be grown at Sapphire, because that's very interesting. And we're talking about South Florida, guys.
So it is quite interesting. In South Florida, they're going to be growing Atlantic salmon, which is a cold water species. That one facility is said to be able to produce roughly 20% of the domestic supply for salmon. So it's quite large farm. It's 9 acres under roof. It's quite a large facility to be under one roof. And it will be interesting to see that company is based out of Denmark. It's another large salmon producing region, specifically an indoor RAS system. So the company has already been quite successful with their designs. So they're not coming in blindly to try and do this. They have a successful track record with which they're built on. So it'll be interesting to see how well they do, but I'm pretty confident that if anybody can do it, they can do it. Anything else? Any comments, questions on the system?
Hold on just a minute.
What kind of fish do y'all produce?
We've been working with 2 different bloodlines of tilapia, and we also produce hybrid striped bass. We're probably going to phase out some of the tilapia and continue to expand on the hybrid striped bass. And the main reason for that is just pricing. It's difficult, at least in Central Florida, to compete price-wise with the wild-caught tilapia market. Wild tilapia, believe it or not, there's enough reservoirs in Central Florida that people are actually going out and harvesting tilapia from the lakes to be sold, and they're quite cheap. So from a pricing standpoint, it's not really cost competitive for me to grow tilapia because I can't compete with the local markets. So we're going to focus more on hybrid striped bass. We've been doing some research with a particular bloodline of tilapia. It was quite interesting. A typical culture cycle for tilapia might be anywhere from 200 to 275 days to go to about 1.5 pounds. That's quite typical for most commercial bloodlines. There is one company that, believe it or not, it's actually a genetic company. It is not a GMO, and I'll repeat that. It's not a GMO. It's just good breeding practices. The work that we've done with that particular bloodline, we've been able to produce 1.5 pound fish in roughly 125 days. So it's a significant improvement in cycle time.
Which species of tilapia is that?
It's Nile. It's a pure Nilotica. But they call it, the bloodline is referred to as GIFT, G-I-F-T. It's genetically improved farm tilapia. It was a program started by the Food and Agriculture Organization in mid-'80s to develop aquaculture in third world countries. So they developed the bloodline for particular traits. They abandoned the program after about a decade, and a couple of genetic companies actually bought the bloodline and have been maintaining it since then. So it is commercially available, but from a production standpoint, you can literally produce twice the amount of fish in the same amount of time. So it's been quite interesting.
So later in the summer, we're going to be meeting with Gino Evans. You must know
Yes.
the Evans farm. And I believe I know they're raising tilapia, but I think it's in their big reservoir pond, correct?
I'm not exactly sure with how he manages his facility. I think he grows a couple different kinds of fish.
You're right. He does. But I think the tilapia production is pond based.
Yeah. Right. Any other questions?
Well, I think, since these young fellows are also maintaining a small recirculating system, and we talked about the needs for water quality, do you want to just quickly, if you don't mind, review some of the optimum ranges you're obtaining in your system and monitoring for things like pH and ammonia, et cetera?
Yeah, so no, that's a great question. We actually have a full water quality lab. It depends on what's going on. So I don't want to speak in absolute terms because Things vary whether it's a brand new system, if it's an older system that's been in production, things like that. So we typically only measure water quality twice a week. We have photometers that we'll use and we'll take water samples to measure specifically things like alkalinity, total ammonia, nitrogen. We also have specific, if you look here on the wall, this controller, we have several sensors within the system itself. So we can monitor oxygen, pH, conductivity, and temperature 24/7. That's measured real time. So I don't necessarily have to measure those parameters in the lab because they're measured real time within the system. That's kind of why we can get away with the actual laboratory analysis on a less frequent basis, because several of the important parameters we're monitoring in real time. So as far as levels go, you mentioned earlier in the presentation, we're actually cycling our systems right now. So we're in between harvests. So we just finished harvesting both systems within the last few weeks. So we shut them down. We're cleaning them out and then getting them restarted. So we're cycling that biofilter now. So while we're cycling the biofilter, we may check water quality once and sometimes maybe even twice a day just to see how the biofilter is performing. But as far as what we're measuring, temperature is critical, salinity, pH, all those things are affecting the toxicity of ammonia. So we'll also measure alkalinity. Alkalinity is a critical one for us. We do have to add sodium bicarbonate to the systems. We add it every day. So we do keep pretty close tabs on that. But we're, with familiarity with the systems, the longer you manage the systems and the more cycles you've had through them, the better understanding of your water quality and how the system performs. That's kind of just experience with the system and understanding how frequently you need to measure certain water quality parameters. I wouldn't necessarily suggest other people do the same things that we're doing, but we're quite familiar with our systems. We know how they respond. We have a pretty good idea on how much alkalinity we need to add each day, and that value varies depending on how big the fish are. So there's a lot to be said for individual experience with your system, because all the systems are going to operate slightly different, but having a good understanding of how your particular system works and how it responds chemically, you just kind of have to get a feel for it. But in answer to your question, I guess, we generally maintain pretty good water quality. Our oxygen levels are usually averaging about 8 or 9. Because we're using saturators and we generate our own oxygen, we can afford to run at slightly higher oxygen levels. Temperature may vary 25 degrees Celsius for the cooler water, maybe 29 for tilapia. Ammonia typically is less than 1 ppm. We generally run a little bit lower pH, usually 6.8. That tends to keep our unionized ammonia in check. So our unionized ammonia might be usually 0.008. Nitrate, usually less than 1, maybe 0.75. A nitrite, I'm sorry. And then nitrate can be usually up to a couple hundred ppm. It's generally not a problem for us because of the water exchange that we do within our soluble solids collectors. We average roughly maybe 5% water exchange per day. So we don't use a whole lot of water, but that also helps to keep some of the chronic issues like nitrate under control.
Well, thank you. That was a good overview. Now, one thing you mentioned that I'm interested in, because these young fellows here, they actually work part-time from family members or other folks that are involved in the shellfish aquaculture industry here in Cedar Key area. And we do have several hatcheries here. And one of the things we're going to start looking at with our hatchery folks is the alkalinity and pH of the source waters. And we found it working with some colleagues in Auburn University and at LSU that they've had to start now adding soda ash to their system to keep the alkalinity up higher than what they're coming in with their source water, mainly because of riverine influence at times. And so I don't know if you can you show us how you're introducing your sodium bicarbonate into your tanks, just to get an idea of what that might look like? No?
Well, I kind of laugh because
I know
as sophisticated as the facility is, what we honestly do is weigh out the bicarb and just dump it into the sump right here.
That's what I needed to know. It doesn't have to be fancy all the time or complicated.
Exactly. So as complicated as this facility is, the chemical additions are quite simple. Now, we could, if you really wanted to, we could automate that system. We could not really measure alkalinity, but we could put particular pH set points in and dissolve bicarb in a pre-mixed tank, and then use a dosing pump and dose that into the system automatically. So you can make it another one of those, you can make it as complicated as you want or as simple as you want. Generally speaking, simple is better, but you lose, automation and control of it. These systems are quite automated, but that particular aspect of it is simple. We don't,
That's good to know.
it's not automated, but it could be.
Is that sand in that filter?
It's not. It's actually a plastic media. It's maybe slightly larger than a pencil eraser. It looks like a drinking straw, but it's shaped like maybe a wagon wheel with spokes. And the reason for that is it has a high surface area per volume. So usually biological media is rated square feet of surface area per cubic foot of material. And the higher the surface area per cubic foot of material, generally speaking, the better the media is. So this particular media, it's kind of, I heard you guys mention bio balls. It's kind of like that, but maybe much smaller. But yeah, it's a plastic media. Do you guys have any questions about the systems that you currently have? Something you're having problems with or anything like that? Anything I can help you with your systems?
Where do y'all get y'all's water from?
We have a well. So our well, I want to say, is only about 100 feet deep. It's not very deep. We don't use a whole lot of water, so it's a relatively small well. Water quality wise, it's okay. We have a little bit of iron. The pH is acceptable. Alkalinity is acceptable. We really don't have to do any pre-treatment to our well water. We're lucky in that aspect, in that the only real issue that we have is with the iron, but for us, it doesn't really cause any problems. So we're fortunate that we don't have to pre-treat our well water, but a lot of facilities do have to bring in water, store it on site, treat it, and then use it. But we're lucky that we don't have any pre-treatment requirements.
So I think they just set up their system at the end of the school year. Is that correct? So I think with the start of the new class, with new session in the fall, they may get their hands full on how to maintain tilapia in their system. Are there any other questions of Mr. Bryan? Well, we appreciate the tour. It's really fascinating to see, and we have advised them as to where they can go online also to play around with that and view the system. With that, I guess we'll thank you so much for participating and informing these young students about recirculating systems.
All right, sounds good. Thank you.
All right.